This problem is about the Compton effect, and it reads: the X-rays detected at a scattering angle of theta equals 163 degrees have a wavelength of 0.1867 nanometers. Find A, the wavelength of an incident photon, and then the energy of an incident photon, then the energy of a scattered photon, and the kinetic energy of the recoil electron. And again, this is a picture from the book. And the Compton effect, not again, but the Compton effect is that we have a photon hitting an electron. It's kind of like billiards. So here's the particle, the photon, that hits the electron, and we would have to imagine it off center, and then the electron goes off, and the photon goes off with a longer wavelength that is less energy because the electron took over some kinetic energy. What I meant to say with the word again is that again we're looking at photons here, but the picture that we get is that of a wave for the photons with the energy, frequency, wavelength actually given, which obviously is the description of a wave. I'm not discrediting at all the particle versus wave duality, but what I'm saying here is it's kind of funny. We're looking at photons, we have to consider photons, but yet we're getting a picture of a wave. Oh well. This Compton effect is another way of looking at that light has to be a photon, and that's where you get that wave particle duality from, because this one here cannot be explained in terms of a wave theory, and indeed we have to go through the motions of the energy and momentum conservation, as I did in a previous problem as I was talking about the Compton effect during relativity. So we have to look at the conservation of energy and the conservation of momentum, in this case here in 2 dimensions in the x and y. So we're actually coming up with 3 equations, and we also have 4 variables actually, which is the wavelength or energy or frequency with which the photon is scattered, then we have the angle with which it's scattered, then we have the kinetic energy of the recoil, and actually we have the angle of the recoil electron. So as I said, 3 equations here, 1 for the energy and 2 for the momentum, because we're looking at x, y, and actually 4 variables. And it turns out that the equation that is given for the Compton effect, this one here, incorporates 2 of those variables. So here I'm going to write it down. I think I just hit the space bar accidentally. Oh, by me hitting the space bar accidentally, I got 1 page ahead of me. Anyway, so I have lambda prime, that's the wavelength of the scattered photon, minus lambda is the wavelength of the incident photon, equals h over mc, and the m here is the mass of the electron, and speed of light 1 minus cosine theta. So what these 3 equations with 4 variables yield is 1 equation and 2 variables, where this one is an unknown. Oops, and this one is an unknown, and I underlined the wrong thing. It's the other wavelength. So the angle is an unknown, and the wavelength of the scattered photon is an unknown. And if we keep this one here fixed, in the problem it says 163 degrees, I believe, then we can figure out what this one is. So we're actually coming out with a function here out of this system of equations. And then, as I said, I did a problem before for special relativity where I had mentioned that in order to arrive at this equation from the energy and momentum conservation, if I notice that the mass of the electron here increases due to its speed, so the mass increase, then I come up with this correct equation. If I disregard a special relativistic effect, then I come up with another equation. Looks more complicated, that's no big deal, but it comes up with results that are too far off from what is being measured experimentally. In any case, that's actually what we would, this equation is actually what we need to figure out the first part. So in part A, we determined what lambda is. In this case, they tell us actually, hey, figure out not what the wavelength of the scattered photon is, but figure out what the wavelength of the incident photon is, lambda. So it's going to be lambda prime minus HMEC times 1 minus cosine theta, and then equals, and that should come out to something in nanometers. This one here is given in the problem as 0.1867 nanometers. This one here would be Planck's constant, 6.626, 10 to the negative 34. This one here is the mass of the electron, that is the rest mass. That's 9.1 times 10 to the negative 31 kilograms. Here 3 times 10 to the 8th meters per second. And then parentheses times 1 minus cosine 163. Overall, you would come up here with something in meters, so just multiply that with 1 times 10 to the negative 9, so that you subtract nanometers from nanometers and overall get nanometers. Just to give you an idea how much that is going to be, is I'm going to go to this link here. I go to an applet that I found at the University of Warwick in Coventry, England. And for example, I'm going to run this one here, and then you can see the photon being scattered, and then here goes the electron, and then I reset, and you can see what happens if I change the angle. Then the wavelength here of the incoming one versus the wavelength of the scattered one change, and then we're supposed to be at 163 degrees. Notice I think I can only go up to 160 degrees, so I'm relatively close. And then here I can change the wavelength. Notice that when I change the wavelength, these actually don't change. I mean, here, yeah, the number changes here, but here it changes just as much. And that what that means is that if I am incident at 0.40 nanometers, then what is being scattered looks like 0.0446, so 46 larger, right? And that would be already in femtometers. And if I'm here at 0.070, notice that also says 0.0746 approximately. So notice that 46 here in the back, and compare that to what is given in the problem, where lambda prime is given as 0.1867 nanometers. So subtract here that 46 that I had mentioned, and you come out with 0.1821. In that neighborhood is where the answer is going to be. Of course, the wavelength of the incoming photon is smaller than the wavelength of the outcoming the scattered photon, because the energy is inversely proportional to that. And that's the next thing they want to know. I'll change back to blue here. So the energy is Planck's constant times the frequency, respectively since they give us the wavelength, it's Planck's constant times the speed of light divided by the wavelength. And let's see, what they want to figure out is energy of the incident photon. So I wrote it correctly here, and you would come up with something in joules. Make sure that at this point you consider this the wavelength here in meters, which means take the nanometers here and multiply, or whatever you come up here, multiply with 1 times 10 to the negative 9. In part C, what they want to know is basically the same thing, but this time around the energy of the scattered photon. So this is the way it looks like. E equals hc divided by lambda prime. There we go, in joules. And in part D, we're supposed to come up with is the kinetic energy of the recoil electron. Well, that's really easy. Kinetic energy of the recoil electron. I mean, it would be 1/2 mass times velocity squared, but nowhere in here do we figure out what the velocity is. But, of course, with the conservation of energy, just out of the picture here, conservation of energy means that the energy of the photon that comes in equals the energy of the scattered photon plus the kinetic energy of the electron. So kinetic energy of the electron is the energy of the incident photon minus the energy of the scattered photon. And I guess I could have written here E prime. There we go. And both of these are in joules, so this one here is in joules as well. This problem is about de Broglie waves. And before I read the problem, this is kind of, this name looks like it would be hard to pronounce, and in fact it is. For years and years I simply pronounce it as de Broglie, figuring maybe that's the French pronunciation, and then I just looked it up and I believe it is de Broglie. In any case, the problem reads: the interatomic spacing in the crystal of table salt is 0.282 nanometers. This crystal is being studied in a neutron diffraction experiment, similar to the one that produced the photograph in this chapter. How fast must a neutron be moving to have a de Broglie wavelength of 0.282 nanometers? Louis de Broglie came up in the 1920s with the idea that if photons exhibit wave and particle properties, then particles such as electrons and protons and neutrons, the latter actually being discovered a few years after, he came up with his hypothesis that particles should also have wave properties, and that's where this idea originates from, and turns out he was correct. De Broglie wavelengths are used for electrons in orbits around the nucleus, respectively, in certain experiments for electrons and other particles as well. In this particular problem to ask about the neutron. So an experiment was devised by Davidson and Girma a few years after de Broglie came up with the idea, where they used a crystal and they fired electrons at that crystal and noticed that they get an interference pattern as if the electrons were particles. I pulled that up here. I made a Google search for de Broglie diffraction pattern, and that's what I came up with here. So here you kind of get a diffraction pattern as if electrons, neutrons, protons, any kind of particles were a wave. FET, Physics Education Technologies, has this one, and again this one here is easy to find, we're just go to physics and then quantum phenomena, and then I believe you have to scroll a little bit, and there it is. There's the Davidson Girma experiment. And so what this one does here is fire the electron gun, and then you kind of see this interference pattern, and it imagines that out of this electron gun there is like this cloud or particle of electrons coming out, and when they hit the crystal, then all these electronic waves are interfering, and sure enough the result looks not that much different from having, for example, sound waves that are interfering. Why a crystal? Well, for one thing, the atoms in a crystal are very nicely aligned, very much structured at equal distances. And then the other thing is that they are really close together, because they need to be, their distance in between needs to be in the order of the wavelength of the particles. I pulled up this diagram here from a much previous chapter on thermodynamics, where it shows the molecular speeds for molecular oxygen, and for example at room temperature that would be 400 meters per second for oxygen molecules, and I calculated that oxygen molecules at room temperature would have a random wavelength, so to say, of, let's see, 0.032 nanometers, while electrons at that temperature would have a wavelength of 10 nanometers. So much smaller wavelength than what visible light has, and therefore in order to see any kind of interference phenomena, any kind of wave phenomena, the particle differences have to be in the order of what the particle's wavelength would have to be. And the problem itself shows that it says that assume that the interatomic spacing in the crystal of table salt is 0.282 nanometers. By the way, also on the side, that number of 0.282, so let's see the spacing here, is given as d equals 0.282 nanometers. That could be computed by taking the density of table salt and looking at how much volume it takes up, and then dividing that by the number of moles in there, and taking the cube root because it's three-dimensional, and coming up with that. Yeah, indeed, the spacing between the crystals has to be 0.282 nanometers. And again, the reason for this one here is that the wavelengths of particles such as molecules and electrons are in that neighborhood for normal temperatures. Okay, and finally to the problem. The calculation is actually really simple. It says that the wavelength equals Planck's constant divided by the momentum of the particle, which is Planck's constant divided by the mass times the velocity of the particle, and we may contrast that with the way it looks like for light, where the wavelength equals c over speed of light divided by the frequency. So for a particle, it depends on the mass of the particle, the wavelength depends on the mass of the particle and its velocity, and of course the velocity for a particle is quite variable, while for light, of course, the velocity is fixed as the speed of light, and what is variable is the frequency. And of course the photon does not have any rest mass. Anyway, I just put this here on the side to contrast the two, but for the problem itself I will take it off. Okay, then it's just a matter of one algebra step here because they actually want us to figure out what the velocity is of that particle. So it's going to be h Planck's constant divided by the mass of the particle and the wavelength. And the wavelength here, as the problem says, I think I moved this down a little bit here, there we go, is given as the spacing between the atoms in the crystal and then the mass, of course. Let's see, these are neutrons. Yeah, so mass of the neutron. And plug these numbers all in standard units, and you come up with the velocity in meters per second. And the result, or the given 0.282 nanometers, is not that much off from what I said earlier about the wavelength of particles at these kinds of temperature given here, and it would be, of course, the random speed. So the result over here is also going to be kind of around here.